of inverse trigonometric function. If we have to define this, the inverse of sine x, the inverse of sine x will give us inverse of sine x will give us 1 over the square root of 1 minus x squared. So the inverse of cos x will give us minus 1 over square root of 1 minus x squared, and the derivatives of inverse of tan x will give us 1 over 1 plus x squared. The derivatives of the inverse of cosec x, this is cosec x. The inverse of cosec x will give us minus 1 over x, the bracket open x squared minus 1, and the derivative of inverse of sec x is 1 over x on the square root of x squared minus 1, and the derivatives of cot x dx is minus 1 over 1 plus x squared. So these are the just terms and figures that you must know offhand. So any times you are given a question, you know the values. You just have the values and how you use it to interpret any of your questions. Let's try to solve a question. Maybe for example, we were given a question like maybe we have y is equal to 1 over, let me write it again please. Y is equal to 1 over the arc sine of x. Now what do you observe here is that you try to rearrange the value of y. You can still write the y as arc sine x all raised to power minus 1. If you're able to see this, it has now formed the quotient rules. And finding the y, the x at these junctions is the y, the x, this one will come down, minus 1 arc sine x onto minus 2 dots. It's a functions of a function, as we have explained early. It now be the derivatives of arc sine x onto the x. So therefore we have something related to we have minus onto sine arc sine x onto minus 2 dots. So you have to go back to the derivative of arc of sine. Arc sine, you see it from here. It is 1 over the square root of 1 minus x squared. So just rewrite it in that form. You said 1 over square root of 1 minus x squared. So from this, it can be written as this minus 2 can come down to have something like the total 1. Everything can fall in denominator. Because of minus, it will make it to come up down, and you can put, we have minus 1 already in the values of the question. You just put minus here. You put arc sine x squared and square root of 1 minus x squared. So you don't need to waste much of your times. This is how we solve the arc sine, the arcs of an angle the second functions. So this is derivative of, let me just have only one example. I'm only just using this as a revision part, because there's an exactly area where we want to use this, and the area is the hyperbolic functions, the derivatives of hyperbolic functions. So now let's have an example, another example. Maybe we are given a question like, you said, if f of x is x arc tan root x. So the meaning of this is x arc tan root x. This is what it's just trying to rewrite here. So how do we solve this? What are the logical terms that we need to solve these questions? Remember that this is a product rule. This is U V. Yeah, so you have to apply the laws. Let's do revisions about the product rule. If y is equal to UV, you know that the y, the x is equal to v du dx plus u dv dx. So now in product rule, the first thing you do, we are to find the f of 1 prime. So this is you firstly leave the one and differentiate the other. So let's pick x for the first and differentiate arctan x. How do you differentiate arctan x? Before that, let me rewrite it better. I don't need to rewrite, because I just want to rewrite that the root x is the same thing as s raised to power half. So now, x dot derivatives of arctan x, is split into two. The first thing is, let's go back. What does it talk about in the derivative of arctan x? Let's try to do something. Maybe I don't want to have a shortcut of solving this. So let's differentiate this first. So, this is our v. Let's say, you can rewrite like this, into, is root x onto x raised to power half. So if you are to differentiate something relating to this, maybe we want to have v prime. The first thing you do is that you go back to the arctan is 1 over x plus x squared. So is this, we said 1 over 1 plus x squared, something like this, dot derivative of x raised to power half, because it's a quotient rule. This is just what I want to put in place. And I want you to know much. So our x is x raised to power half already. So after that, you have to differentiate again. So let's say we have v prime, we have 1 over 1 plus x, because 2 half we multiply 2 dots. Now 1 over 2 onto x onto minus half. Remember that you are going to subtract 1 from this. So you have, we can now rewrite it as, this one will come up x raised to power minus half, x raised to power minus half. The 2 will multiply 1 plus x. So the derivative of the v prime. So that is just the derivatives. And so I'm able to let you, so this is what is making me to come down a little bit. I want you to understand how derivative of arctan x root x be this. So let's now apply our quotient rule now in differentiating this. You know, you have ever getting the value for this. So let's apply the quotient rule to, you now have dy dx is equal to, now you select x dot derivative of arctan x root x, give us this. So don't need to waste much of your time. Give us x to the power minus 1 over 2 over 2 onto 1 plus x. So that is what I just want to put in place. Now, plus, you differentiate x, you leave arctan x, z, plus, when you differentiate x, give you 1, and you leave arctan root x. So recall that this is raised to power 1 already, that our dy dx is now, so 1 plus half, you have minus half and you have 1 to give us s raised to power half over 2 onto 1 plus x plus arctan root x. So the final answer now is root x over 2 onto 1 plus x plus arctan root x. So this is just the final answer. So this is final answer. So let's also have another example. Maybe we were given a question like, you said the g of x is arc sec x squared. So if you are to find the derivative of g of x, you have to go back again to the, you see the sec is 1 over x root x squared minus 1. So that derivative of sec is, there is x 1 over x squared minus 1. So if there is 1 over x onto the square root of x squared minus 1. But to recall, something happened here which you need to know. Let me rewrite. Recall that our x now is not ordinary x, it is s squared. So now give us 1 over, so instead of writing x, you now write s squared onto square root of 1. Sorry. I want to write it better. So you now write 1 over x squared square root of, it is s squared minus 1. So, but the value here is not x. So you now put x squared or squared minus 1. Now dot the derivative of inner give us 2x. That's all. This is just, I just want to explain. So now you discover that the x cancel x here, mean that g of x is now 2 over x onto square root of x raised to power 4 minus 1. So that is all. So that is only 2 examples in the second derivative. So we are going to another subtopic, the real life applications of this subtopic. Where does it rain? How do we use it, and others. We just want to have a little applications of first and second derivatives in calculus, and so the application, for example, we're given a distance is f of t and t cube minus t squared plus 9t, and recall that if you are to find the velocity, the v of t will be the x dt. So the velocity here is 3t squared minus 12t plus 9. This is the velocity. So maybe you now say that what is the velocity after 2 seconds? If our vt is 3t squared minus 12t plus 9. So what they are to find is in the 2 seconds, we have minus 12 onto 2 plus 9, which is equal to 12 minus 24 plus 9. So 12 minus 24 plus 9. Let me go back so you can write. So you just put it, and by the time you put the value, our answer is 12 minus 24. You see, have minus 12. Minus 12 plus 9. We have our v. It is now minus 3 meter per second. So at time 2 seconds, our velocity is still low. We have minus 3 meter per second. This is just the applications of the derivatives in natural science, especially in science. I'm still going to do the one of natural science, but let me just solve a little part here. I'm just go straight to economics part. Now, we have able to get the velocity after 2 seconds. Let's now trying to find after 4 seconds. So what you need to find here is after 4 seconds, and you know that in after 4 seconds, we have 3 onto 4 square minus 12 onto 4 plus 9. So that is 3 times 16. You have 3 times 16 minus 48 plus 9. So to give you 48 minus 48 plus 9. So to give you 9 meter per second. So that is just the value. So we also have something like when we say when the particle at rest. If the question say that when the particle at rest, and you know that you are able to get a value of v, our vt is 3t squared minus 12t plus 9. So at rest, v of t is equal to 0. That's just the meaning, because there is no movement at time 0. So the velocity at rest, there is no velocity. So therefore, the velocity is 0. So if the velocity is 0, meaning that 0 is equal to 3t squared minus 12t plus 9. So you write it in quadratic form, plus 9 is equal to, let's reduce by 3. We have t squared minus 3 divided by 12. We have 4t plus 3 is equal to 0. So what are the two numbers? In solving this quadratic equations where we have t squared minus 4t plus 3 is equal to 0 can be written as t squared minus t minus 3t plus 3 is equal to 0. T is common, t minus 1 minus 3 is common, t minus 1 is equal to 0. T minus 3 to t minus 1 is equal to 0. So t minus 3 is equal to 0, or t minus 1 is equal to 0. T is equal to 3, or t is equal to 1. So at rest, Vt must be 0 at t is equal to 3 seconds and a second. So that is when they are talking about when a particle is at rest. I will just try to illustrate. Where we are going to now is how does this applicable to economics part? The economics part, that is the cost of productions and others. So, for example, we were given maybe a cost of productions. They used to represent in this form like a plus bx plus cs squared plus ds cubed. So this is the form it's used to represent. For instance, suppose a company has estimated that the cost in dollar of producing X item, maybe they want producing $1 is this. The cost of item used to produce $1 is 10,000 plus 5x plus 0.01x squared. So they said during the X item, so X represents items. He said, for instance, suppose a company has estimated that cost in dollars of producing X item is this. Now, the marginal cost value, the marginal cost function is so the marginal cost is, it will now give you the second of options of the cost of the item. So the marginal cost function will give you the derivative of this. So in define this, give you 5 plus the 2 will come, it will be 0.02x. So that's all. So now the marginal cost at production level of 500 items. So let's see the marginal cost at the production level of 500 item X. So we want to know the production cost at 500 item. I've represented that X represents item. So the marginal cost so let's now put 500 into the equation. Let's put you are putting 500 in the derivative. We have 5 plus 0.02 onto 500. So by the time we're able to multiply this in dollar, when you try to do this, 0.002 should be This will be 10. That is how it will be. So everything will now be $15 per item. So the cost, that's what we mean by marginal cost. So the cost will be $15 per item. So that is all. So this is in doing the applications in economics or in any ordinary sciences, it does not really cost much in practical way of that math, but they only just want you to have the applications, the basic knowledge of what we are doing basically in calculus, so you're able to use it in your practical days. That's just the reason why we were given all those analyses. So I will still go further to solve more questions, so you're able to get it better. Growth and decay. If y of t is the values of quantity y at time t, and if the rate of change of y with respect to t is proportional to its size, y of t at any time, then dy dt will give you ky. But this y, it is what we have been talking about here, that y is y of t. It means the value of quantity at a particular time. The value might be changed at a certain time. At an increase of times, there is tendency for the value to change or to reduce. It depends on the number of times. So everything's at its own time. Now, he said any exponential function of the form y of t is constant exponential kt, where c is a constant satisfying. By the time you differentiate this, you have dy dt. The c is constant, dk will multiply this in exponential differentiation if you're able to go back to what we have able to have done. Now give you k cet. You know, this cet kt is also the value of y. Any function that satisfies the y dt that give us ky must be of the form y is equal to c e kt. So, for example, you were given the y of 0, which is equal to c, meaning that initial value of the function. So every function given to you must have an initial. So initial value is at when it is 0. So the only solutions of differential equations, the y dt is equal to ky, are exponential function. So the theory now says that, this is the theory, you now say y of t is equal to y of 0 ek. So this is the theory. At any time you are having an equation that satisfies the y dt is equal to ky, the constant y, giving a constant value, meaning that y at a particular time, it is y of 0, that's initial value, onto ekt. So now what talks about the population growth? The population at a particular time is the size of population at a time t, meaning that the derivative of the change in population per period of time will give a constant p, or dp slash dt divided by p is equal to k. These are the quantity. So for dp dt, for example, we're given something like our dp dt give us 0.02p, meaning that p on its own is p of initial value onto e onto 0.02. So you have to understand these logical terms. So anytime you are given the p dt is 0.02 or any value to be multiplying that value, like constant value, the y represented by y, so p, the p of t will now be p naught onto e 0.02. So let's see an example. Let's read out this question. It said, use the fact that the world population was 2,560 million in 1950 and 3,040 million in 1960. So this is between 1950 and the 90, just the 10 years. To model the populations of the world in second half of the 20th century, assume that the growth rate is proportional to the population size. What is the relative growth rate? Use the model to estimate the world population in 1993 and predict and to predict the population in year 2025. So if from here we assume that the time t in the year and let t is equal to 0 in the year, he said let t is equal to 0 in the year 1950, in year 1950. So if t is 0 in the year 1950, now you know we are given a population in time t. So let's assume population at 0, that is initial, is the initial is 2,560 million. That is the population at 0, which is due to the fact that the world population was this in 1950. So now in 10 years period again, in 10 years time, it is 3040 million. Now, what do you now want to do? Recall that the population per time is given as constant p. Now, let's now analyze this question better. At B0, that is initial value, is 2,560 million. In 10 years' time, is 3,040 million. So, let's have like the P of t is now P of 0 onto E constant t, which will give you initial value is 2,560 E of kt. Now, and at the same time, the P of 10, the population at in 10 years times, now give us because we have already have the initial value to be 2560 e raised to power k is now 10. Time is now 10, sorry. 10k is equal to 3040. So you now say that exponential 10k will give you 3040 over 2560. So you can write you have 10k to be equal to ln 3040 over 2560. So we want to find the value of k. So the value of k will be, you divide both sides, you said k is equal to 1 over 10 ln. Press your calculator to get the value 2560. So the ln, you firstly divide this, you find the logarithm value, you now divide by 10. So by the time we divide by 10, we're able to get the exact constant value now to have 0.017185. So this is the value of K. So what is now the relationship between them? So we want to write. So if you're able to see that, you see that the K can be represented in percentage. Let's try to represent in the percentage. Let's have like K is equal to 0.017. So it can be written as 1.7 over 100. So which is 1.7% increase. So now the real equations now give us 2560 e exponential 0.017185. So this is a general equation for the populations of the question given. Now we have been getting the general equation, but we want to estimate the world population in 1993. So if you now want to get, since you are able to get the value of the equation, so in 1993, so from 1993 you calculate to from 19, the initial value is 1940. Is it 40? 1950. Good. So between that time we have 43. So we have 43. So this is of t. So we now have 2560 exponential 0.017185 multiplied by 43 of time. So since you are able to get the value, so the estimated value after multiplying this will be 5,360 million. So what make it a little bit difficult is the first one to get is the one that you need. So since we are able to know the equation to be 250, the P of t is 250 60 exponential 0.017185 t. So now let's estimate for year 2025. Let's estimate the population of year 2025. So from 1950 to 2025, we give you 75 years. So our time is 75. And you know our equation to be, so P of 75 will be 250 E onto 0.017185 onto 75. So the P of 75 will now be, so by the time we try to approximate, we have 9,289 millions of population. That is all. So that is how we find. So you just have to watch the video times again to get it better if your first view does not get it at once. So I would just advise to watch it again and get the logic term. So you firstly find the constant. How do you find the constant? The initial values and the values at the period of times will make you to get the constant. As you're able to get the constant, it's very easy for you to get at the value of 43 of each period and estimated at 75 at year 2025. So if you're opportune to watch this video, we use the opportunity to tell you that subscribe to this our channel so you can able to gain more as we are releasing more video. So thanks for watching.